Hello everyone. Today we're looking at problem number 909, which is snakes and ladder. In this problem, we are given a 9 by 9 matrix and the values ranges from 1 to n squared. And the numbers are arranged in bootstrap-feeding method, which says that the the orientation alternates. So if in the first line or the bottommost row, if you're going from left to right, then in the row above that, you're going from right to left, and it alternates like this. Okay, so this is the arrangement of the numbers, and what you have to do is you're gonna use a dice. Okay, and so you're gonna have a throw of dice here, and based on that, starting from this position, you can go to one of these numbers, and what you have to identify is what is the shortest distance to reach the n, which is the nth squared element. And it need not be always here, it could also be on the other side. Let's see what else. So yes, we are always starting from a particular number. We are always looking to go to another step, which is in the range of card plus 1 till plus 6, and the max is n squared. And yes, a very important point, some of the cells can have, let's say, a ladder, or some of them can have, let's say, a snake. Okay, what that means is that if you reach here, your destination is this particular point. So what will happen is that this destination will be given to you here, and I will tell you how all of that is encoded. Now, in case of a snake, if you reach here, your final destination is there. So at this cell, you will find the value of 11. Okay, so these are the cell numbers, but this is not what is given to us. So what is given to us is a matrix, okay, where most of the values are -1, and the only alternate is having some value here, x, which means that this is the destination. If it is a snake, you're probably going back. If it is a ladder, you're going forward. Okay, but this is the number that you have to jump to if you end up coming to this particular cell. So that's the problem, and that's what they say next. That the board. So we've been given this input, which is the board, and the row and C of it. If it is not equal to -1, then we have the destination given in this place. Another important point, we should take every cell just once. Like it is possible that I have some sort of a loop, like for example, from here I go to a ladder, and from there I um, come back using a snake. Okay, like this. So it is possible like that. We have to avoid the loops there. And the return that is expected is the least number of dice rolls required to reach the destination, and we have to return -1 if that's not possible. Okay, so let's start thinking through this, right? And there are a bunch of approaches that we can do. I'm going to talk through one of the approaches, which is going to be a dynamic programming one, but we're not going to be implementing that, and I will also tell you why we're not going to be using that. I'll share all the thought process here, but let's first look at the dynamic programming approach. Okay, so let's try to code this up as like a recursion. So now, if you think about it, let's say you have the recursive function, say it's called recursion, and you have some node ID here. And let's say you also have DP here that we're starting with. Okay, so what are the end cases, right? If the node ID, okay, has gone to greater than n square, that means I can never reach that step, right? I can never reach that cell because that cell does not exist. So in terms of the step count that I want to add to this path has to be like a really large number so that I never pick this. So let's return 1E9. What is the other edge case? This is a positive terminal case, right? So if node ID itself is equals to n square. Um, can you note this is a little bit of a pseudocode because I'm writing n square and I've not defined all of the other things defining the n and the n square. But this is to tell you the logical flow, so you can ignore some of these details. So the next terminal case is the positive one where node ID itself is n square, which means we have reached the terminal state and I don't need any more dice rolls from here to reach n square. I'm already there. Okay, so for this we can return 0. Okay, these are the edge cases. Now other than that, if you are anywhere on the board, from here you can take one of the 6 steps. Okay, you can take 1, 2, 3, and you can take any of the 6 steps. Okay, so what that means is for the next step in range of, and this is what we saw also in the question, right? So they had given us that we should represent it as this, which is exactly what I'm going to write. Okay, so we're going to say here in the range of what is the starting value. So starting value is node ID plus 1. I can either take that or I'll have to take minimum of node ID plus 6 or n square, whichever is minimum, and then plus 1 because I want to have those values. And this will tell me what are the other next state possible. Oh, another thing. If a node has been already visited, I don't want to visit it. I don't want to do the work again because there are multiple routes to reach one node, right? We're taking multiple jumps, jump of 1, jump of 2, and so on. So if node ID in DP, let's return that value, then and there it's no need to do the repeat work. Okay. Now, when this happens, the only thing that we have to check about is if this next step is if the value of this cell is actually -1 or if it is equal to some other value. Okay, so let's say we have some method which does the conversion for us and which gives us R and C. We're going to convert to RC and then we give next step. Okay, so we can check if the next step is equal to board of R and C if board of R and C is not equal to -1. Okay, that means there was a value, otherwise we will take the value that we had identified using the dice rule. And I do this. Okay, so I've done this. Now with this, now I'm going to the next step. Okay, so I'll start another recursion. So child step, maybe let's get the input of the child step. This is the return that we're getting from a step forward, right? So we'll say recursion next step comma dp. Okay, and now what we can do is we want the minimum number of steps that helps me to reach n square. Okay, so let's have a min variable. So minimum steps is equal to 1 E9. Let's say a very large number, so I will say here min steps is equal to minimum of the current min steps that we have or what we got from the child. Okay, and then plus 1 for going to the child. Min steps, the child steps is the least number of steps to reach n square from the child to the n square, and plus 1 to go to the child. Okay, so all of this is done, and then I can return min steps if min steps happen to be less than 1e9, else -1. Okay, so this kind of an algorithm can run into TLEs for large input size, and the reason being, let's say I have to reach this into. There are mul not this. There are multiple steps. Okay, like this, like this. Like go here, go here, go here. Okay, whatever. I mean, not exactly like this. Maybe the the direction is not very good, but you can say like, okay, let's in terms of hop. You hop here, then you hop here, then you hop here, and 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 then there can be multiple such paths. Okay, and so, but what the dynamic programming does is, because it is a depth first approach, it takes the recursive approach. It'll take one node and go till the end to see if it finds n square or not. And then it'll take the next approach, which is slightly altered, and then it'll find all the combinations and so on. And because of which, what happens is that we will be exploring all paths even if they are not the shortest. Okay, so that's the problem here, that we will be exploring all the paths, which in some cases useful in a case where, let's say, you had edge weights, you don't know which edge weights can help you, and so you probably want to try all combinations to see how that works out. But in this case, it is not very efficient because the cost of jumping to the next cell, so we're only counting the number of dice rolls as the cost of reaching n square. So now if you think about another approach, which is breadth first approach, what happens here is that you are from a point doing level order traversal. Okay, and if there is a path where at a particular level you reach n square or your terminal state, then this path is actually the lowest cost path because you have discovered it the first, right? And once you discover this, you're not you can eliminate the other path and you can terminate it there itself, and you can say this is the shortest path. So this is the crux of the solution, and this is what we are going to be also leveraging for our problem today. Okay, I'll explain this logic using the pseudocode only, and I think that should be good enough to work through the problem. Okay, so let's implement the breadth first search approach here. Okay, so let's say that we define a queue and we define a distance of 0 for the first cell, and then the value of that cell is 1. We will also use a visited set here because, like I said, you can reach a cell through different paths and you don't want to do repeat computation, so we will use this. Okay, so next step is while q, you pop out that and you get distance comma, let's say node id q dot pop from the left hand side. And now what we do is we check if this node id is equal to n square. Then we return the current distance and we don't proceed any further. If that was not the case, then we want to roll the dice. Okay, so we say for destination node in range node ID plus 1 comma minimum of node ID plus 6 or n square, and then finally plus 1 because we want to take the last value of this, and this gives you the destination node. But there is a chance that the destination node has either a ladder or a snake at that point. So we need to convert it to row and column so I can check the value. So let's say I have a supporting function which says convert to row and column, and you give it a ID. Okay, and once this is there, then we just say that destination node is equal to board of R and C if board of R and C is not equal to -1, else we will take what we had gotten from a dice row. Okay, and if this particular node was not already visited, so if not in visited, then we will say that okay, let's add it to the queue. Okay, when we add it, we will have to increment the distance plus 1, and then we will say destination node, and we will also mark it as visited dot add destination node. Okay, and so this code should ideally reach n square and return this, but let's say for some reason, because of a snake or multiple some configuration like that, I am never reaching n square, but I am always reaching another cell which probably got already visited, then Q will get exhausted, and in that case I can finally return -1. So this at its very high level is our binary search approach. There is a small nuance of how we're going to convert the ID to row and column, so let me maybe talk about that a little bit now. Okay, so there are two ways you can do this. One of the ways is that you take some extra space to make that simpler, and this approach is actually quite useful because if it helps you eliminate mistakes. And if you think about it, your visited is already taking order of n square space. If you take additional space to map these row and columns to ID, you're just taking another order of n square. So you can do the trade-off and see, like, based on the constraints whether it's worth it or not. But in terms of portability, if possible, it's definitely a good approach. So what we can do is we can create a cells list. Okay, these are values from 0. Actually, you can have 0 and mark it as -1, and then you can have from n to n square. So totally you're having n square plus 1 values. Okay, and in this value, what you can do is you can fill your row comma column. So for whatever ID we are looking at, let's say at this point, we are able to retrieve that because we filled it up like this. Okay, and it's quite straightforward, you're not doing much. But if you are not doing this, if you're not using extra space, and if you want to do it on the fly, then it gets a little complicated. It's not complicated in the sense that there's logic to it. It's complicated in the sense that it's quite error prone. So you will have to be just watchful about the steps that you're writing. Okay, so let me tell you what I mean. Metrics. Okay, awesome. Now let's discuss. Okay, so let's say, let me also mark this, right? So if you look at the actual rows, this is starting from the bottom, but the row ID is 1, 2, 3, 4, 5. Same way, 0, 1, 2, 3, 4, 5. Okay, so this particular cell is 5 comma 0. Okay, so now when I get an node ID equal to 1, I need to convert it to 5 comma 0. So the way you can do that is you first look at how, so you know that every row has 6 elements. Okay, and what you can do is if you divide any of these numbers by 6, you should get 0 for this row. Okay, and if you divide by 6, you should get 1 for this row. And you can see that if I divide anything until here, I'll get 0, but if I divide 6, I'll get 1. So one of the things that we can do is align this by subtracting -1. Because of that, we will get 0, 1, 2, 3, 4, 5. Okay, so I'll get these numbers. Now, if you divide this by 6, you're going to get 0. Okay, that is the row ID looking at the starting point, which is here. But if you look at the indexing is different. So what you'll have to do is n minus 1 minus the row that you calculated. Okay, this will be your row dash which you want to return. Now, this was for the row. Now, if you think about the column, what you will have to do is, again, if you convert it like this, right, and if you take the modulus, so 0 modulus 6 is 0. That means it needs to be at the 0th column. 1 modulus 6 is 1. So that means it needs to be the first column. Okay, so this works if we are going from left to right. Okay, so when are we going from left to right? We're going from left to right whenever R is 0, R is 2, R is 4. Okay, at these places we are going from left to right. What happens in the other case? Okay, so in the other case, again you would have calculated. Let's take the example of node ID 10. Okay, so node ID 10. What happens there is, first of all, let me just quickly erase this and compute both R and column. Okay, so if my node ID is equal to 10, first thing is I subtract it by -1. So 9 divided by 6 gives me 1. So that means it's the first row. But this is not really the first row, right? So I'll have to subtract n minus 1 minus my row. So I get 5 minus 1, which is equals to 4, which is where 10 is sitting. Okay, now I need to do the same computation for the column. Okay, so now I say 10 modulus 6. Okay, sorry, I'll have to subtract 1. So I'll say 9 modulus 6. And when you do 9 modulus 6, what do you get? You get 3. 3 is the index. So because what we did was, if you look at this, we adjusted these as well. So you had 6, 7, 8, 9. Okay, 0, 1, 2, 3. This is what it is. Okay, same way, if you look at, let's say, 16. 16 minus 1 modulus 6. Okay, 15 modulus 6, which gives me 3. 0, I get 0, 1, 2, and 3. So this 3 is coming in this direction, and this 3 is coming in this direction. Repeat here. Okay, so we have identified that we have to go 3 plus 1. We have to go to the fourth item. If you are if you're on a row which has which is going from left to right, you can directly go to the fourth place. Otherwise, let me simplify this. Okay, Let's say if you got the position 0, 0 means 0th column. But if your order is reversed, which means you're looking at 0th column, but your 0th column is reversed, so your 0th column is here. So what we need to do is n minus 1 minus a column will give me the C dash. So this is how you can adjust those things, but it'll be a little complicated. So that's about this prompt. Hope this was helpful. Thank you.